Welcome back to the Foundry by Forge College. Today's explainer is all about armoring up your code. We're diving into robust error handling and retry strategies. If you've been following along with our track on deploying on Solana, specifically navigating through the Solana deployment strategies and scripts course, you know we're deep into the advanced deployment strategies module. And today, we're going to teach you how to make your deployments absolutely indestructible. Because let's face it, out in the wild, the network doesn't care about your feelings. It's time to move beyond building scripts that only work in a perfect vacuum and start building ones that actually survive the absolute chaos of the real world. So, think back to our last lesson, mapping conditional deployment flows. We built the absolute perfect conditional deployment map, right? We had branches, validations, rollback triggers, the whole shebang. But here is the billion-dollar question. What actually happens to your flawless execution when a transient RPC node suddenly decides to drop offline right in the middle of your deployment? Well, let's fix that. Here's our blueprint for today. We're covering when deployments go wrong, the magic of idempotency, classifying your errors, smart retry policies, and putting it into practice. Let's get right into it. Section 1. When deployments go wrong, and building the indestructible script. Okay, before we can build our indestructible script, we kind of need to understand the enemy here. We're talking about execution layer policies. The harsh reality of Web3 is that the network is definitely going to hiccup. You're going to hit network timeouts, you will get slapped with rate limits, and temporary RPC node errors will completely ghost you. When these inevitable blips happen, our scripts absolutely need deterministic recovery rules. Without them, you're looking at corrupted states, unexpected rollbacks, and cascading failures across your environments. We need a solid plan. Moving on to Section 2, the magic of idempotency, which is your shield against duplicates. To safely retry a failed step, we essentially need a magic shield to protect us from duplicating side effects. Enter idempotency. I know, it's a very fancy, slightly intimidating engineering word, but the definition is actually super simple. It's the property that repeating an operation yields the exact same state as running it just once. Think of it like repeatedly mashing the button at a crosswalk. Pressing it 10 times in a total panic doesn't spawn 10 little walking men, and it doesn't make the lights change faster. It just safely converges to one desired outcome. Let's make this concrete. Imagine a network timeout happens right after you successfully create an on-chain account, but before your script actually gets the success memo. If your script blindly retries, which is non-idempotent, you're going to accidentally duplicate resources or just outright crash. But if it's inidempotent, it acts like a bouncer. It checks if the account already exists first. If it does, it quietly smiles, checks the VIP box, and moves on. That makes your panic-induced repeated attempts completely harmless. Section 3. Classifying your errors, or knowing when to actually retry. Here's the hard truth. Not every error deserves a retry. Sometimes trying again is literally the worst thing you can do. As you can see broken down in these buckets, we divide errors into 3 camps. 1. Transient blips. These are timeouts that we can just wait out. 2. Stateful issues. These are partially applied operations requiring a graceful check. And 3. Terminal errors. Think invalid arguments or auth failures. For terminal errors, retrying a bad password 1,000 times won't magically make it work, right? The script must fail fast and immediately alert a human. On to Section 4, smart retry policies. We're talking exponential backoff and jitter. So once we identify an error as a transient blip that we actually should retry, just hammering the network in a blind panic is a terrible idea. We solve this with a smart pacing policy called exponential backoff. The industry standard multiplier here is 2.0. Instead of retrying every single second, we wait 1 second, then 2, then 4, then 8. This exponentially increasing delay gives the struggling network some vital breathing room to, actually recover. But wait, there's a catch. If all of your parallel scripts hit an error and apply that exact 2.0 multiplier at the same time, they'll all wake up and retry at the exact same millisecond. To fix this, we add a random variance called jitter. Jitter ensures your scripts don't accidentally DDoS the network. It's a lot like a crowd of people realizing they need to stagger their exit rather than awkwardly squeezing through a single door all at once. Taking a look at this technical specification sheet, you've got your standard tuning knobs. You might start with an initial delay of, say, 200 milliseconds. Then you have your 2.0 multiplier. And critically, a maximum delay cap, so you aren't waiting around for hours between retries. You'll also definitely want a max attempt limit and an overall deadline, maybe 60 seconds. These boundaries ensure your retry wrapper eventually throws in the towel gracefully rather than just looping into eternity. Finally, Section 5, putting it into practice with wrappers and vibe coding. Okay, theory is great, but execution is everything. Let's mechanically apply these tactics around the smallest safe unit of work in your code. You're going to design your deployment steps as tiny, highly testable primitives. For example, using a retry with backoff wrapper that encloses a publish if missing state query. The golden rule here is to explicitly verify the on-chain state before executing any new writes. Always query first and write second. To build this out quickly, we highly recommend getting into an AI vibe coding loop. Step 1, ask your AI to generate those retry wrappers and idempotent primitives. Step 2, run a local test harness to simulate those annoying transient RPC timeouts. And step 3, refine the code. Add in your jitter and your circuit breakers, and keep testing until absolutely no duplicate writes occur during those simulated failures. Now, even with all these safeguards, if things still go wrong, your post-failure triage relies entirely on observability. You absolutely must emit structured logs every single time a retry loops. This includes a monotonic attempt counter, so you know for a fact if it's try number 1 or 5, a correlation identifier to track the specific deployment, and explicit details on exactly how that error was classified. I want you to burn this golden rule into your brain. Treat logging as a first-class citizen so retries are verifiable and debuggable. Rich, structured observability is the absolute only way to prove that your idempotency checks actually stopped a retry storm from causing total chaos on the chain. Without logs, you're just flying blind, and nobody wants that. Armed with this indestructible foundation of smart retries and idempotency, you are ready for the next level. In our upcoming lesson, we're going to reuse these exact same resilient patterns to safely reduce latency, batch operations, and drastically optimize your scripts for speed and efficiency. Because remember, you really can't go fast until you know you're safe. And that brings us to the end of today's explainer. So I leave you with this provocative thought. If someone literally unplugs your RPC node right in the middle of a massive deployment, will your script survive without breaking a sweat? If you're sweating just thinking about it, well, you know exactly what to build now. This explainer was made by Forge College. Please visit forge.college to dive deeper into these programs, explore our courses, and master other advanced Web3 topics. See you next time.